So this is currently the most unknown yet most abundant entity in our universe. Our attempts to even hypothesise what it is are still in their infancy, so what are we doing to learn anything we can about dark energy's nature? We heard a bit earlier from Carole about the information that Euclid is sending back about the history of our universe. But how does that cosmological data further our understanding of dark energy? I've been speaking to Lawrence Berkeley National Laboratory's David Schlegel.
The data about dark energy is only starting to get good now. The only observable that we have right now for dark energy is how it's been pushing on the universe today compared to the early universe.
If that is the only current observable that we have, where do you even go from there? Is there a part of the cosmos you can look at to provide any more kind of insight?
Yeah, no, that's a good question. And for studying dark energy today, because we only have this one observable that doesn't fit, which is the history of the expansion of the universe, it means you can't look at just one part of the universe to make a measurement of dark energy. So I'm in the business of making these giant maps of the universe, these giant three-dimensional maps. If you only make a map of the local universe, I should say for the cosmologist, the local universe is the billion light years nearby. If you did that, that map tells us very little about dark energy. So the data that we have right now, discovery was 25 years ago, but we're still in the early stages of understanding dark energy. So in the intervening years, we've made the measurements that confirm very strongly that dark energy exists and approximately what its influence is on the current day universe. But we don't have very precise data on what's happened between the early universe and today. And so the data right now, it really is, it's confirming the discovery, but not much else. Euclid and this next generation of experiments, what we're doing is making precision measurements of what the effects of dark energy have been as a function of time. And so one of the ways that we phrase this is, has its effects been evolving with time? And so that would be what we would call a dynamic dark energy, where it wasn't the same in the early universe as it is today. We know fractionally in the early universe it was less important, and that's because the universe was more dense. It hadn't expanded as much. So shortly after the Big Bang, the universe is expanding. You have the forces of gravity attracting matter to other matter, galaxies to other galaxies. That's slowing down the expansion. Dark energy was still there, but proportionally, it was only a small fraction of the energy density of the universe. Then fast forward to today. Today, the universe has expanded enough that dark energy, even though it's approximately constant volume of universe, proportionally, it's a much more important effect on the universe.
So by mapping this out and understanding whether or not it's dynamic, would you be able to sort of cross off a few contenders as to what it might be, or might be slightly composed of?
Yeah, no. So the future, I mean, especially if you look at the far future of the universe, we really have no idea what's going to happen. So it appears that the effects of dark energy, it's very close to a critical amount where the universe, maybe it expands forever, maybe it even undergoes a big rip where the whole universe essentially rips itself apart, or maybe dark energy evolves such that it turns off or freezes out. And in fact, there's a glimmer of data just from this year, 2024, that suggests that that might be the universe that we live in, where dark energy may actually be evolving so that it's becoming less important with time, but we don't know yet.
It seems extraordinary, and the part that really bakes my brain is the nature of dark energy suddenly accelerating the universe, about 4 billion years ago. And as you're saying, it might be able to evolve further in the future. It almost sounds like something that uh, has its own mind to make up.
I keep saying this, but we just know so little about it. And when I introduced myself, I could have introduced myself as an expert in dark energy, which unfortunately doesn't mean that much. Like it's not hard to become an expert in dark energy because we know so little about it.
Do you have a favorite idea as to what it might be?
That's a very good question. So what we've been talking about are the current knowns and unknowns in the universe, where the two big unknowns are the nature of dark matter and the nature of dark energy. There is another unknown that we have not mentioned, which is what happened in the first moments of the universe after the Big Bang, where what appears to be the case is that there was an inflationary force that might have been another force very much like dark energy that accelerated the expansion of the universe for some period of time, although in that case, not for billions of years, but just for a tiny fraction of a second. And that homogenized the universe that we see today. And then that force, or whatever it was that we call inflation, turned off. So that's an example of what we would call an inflationary force, if in fact that's how it behaved. So that is yet another force that we think we can design experiments to study actually in the future. But the intriguing thing to me is we know of this other force that we think was dynamic, inflation. There's this force that we see today, dark energy, where we know very little about it. And I guess intriguing to me would be, are these two unknowns or are these one unknown? So in other words, are we talking about the same force? We just see them at different times and we're labeling them differently.
David Schlegel.